Hello, good morning. Today's topic is 16th group. Today's topic is P block elements, 16th group elements. In 16th group elements, we discussed about the group elements, electronic configuration, oxidation states of group elements and their occurrence, trends in physical and chemical properties, dioxygen, its preparation, properties and uses, classification of oxides, ozone, sulfur and allotropic forms, compounds of sulfur, preparation properties and uses of sulfur dioxide and sulfuric acid, and structures of oxo acids. In this topic, we discuss about the group elements, electronic configurations of 16th group elements, oxidation states of elements and their occurrence, trends in physical and chemical properties. Electronic configurations. We know that 16th group elements have NS2 NP4 configuration. In NS2 NP4 configuration, they have two unpaired electrons in valence p subshell. Thus, electronic configurations, the group elements are oxygen, sulfur, selenium, tellurium, polonium. Electronic configuration of oxygen, atomic number of oxygen is 8. So, electronic configuration 1s2, 2s2, 2p4. Therefore, in valence shell, it has two pairs of electrons and two unpaired electrons. So, it has two unpaired electrons in valence shell. Sulfur, atomic number 16 and its configuration 1s2, 2s2, 2p6, 3s2, 3p4. So, in sulfur, third shell is the valence shell. Sulfur belongs to third period. Selenium, atomic number 34, followed by argon 18, 3d10, 4s2, 4p4. So, in selenium, inner 3d subshell is also available. In tellurium, with atomic number 52, the configuration is krypton 4d10, 5s2, 5p4. So in tellurium, 4d inner shell is available. In polonium configuration, xenon 54, 4f14, 5d10, 6s2, 6p4. So in polonium, there are innermost 4f subshell and inner 5d subshells are available. So the general configuration of these elements is NS2, NP4. So whatever the information discussed just now, it is given in the tabular form: oxygen, sulfur, selenium, tellurium, polonium, and livermorium is a radioactive element and it is a transuranic element. It is artificially prepared. Trends in physical properties. Density. Density increases down the group with increase in atomic number. So with increase in atomic number, atomic mass increases, therefore density increases down the group, that is from oxygen to polonium. Melting and boiling points. Melting and boiling points increase down the group. This is because size of the atom increases as atomic number increases down the group. As size increases, the interatomic van der Waals forces increase. So as attractive forces, that is van der Waals forces increases, melting and boiling points increase down the group from oxygen to polonium. Ionization enthalpy. Ionization enthalpy decreases down the group. The reason is increase in size of the atom and increase in screening effect. So because of the increase in size of the atom and increase in the screening effect, the ionization enthalpy decreases. As size increases, the nuclear attractive force decreases over the outermost shell. The atom is not able to hold its own electron with greater force. Under such conditions, the tendency to hold the electron decreases, therefore the energy required to remove the outermost electron becomes less, thus ionization enthalpy decreases. Oxygen has a very high ionization enthalpy due to its small size. Metallic character. Metallic character increases down the group. Oxygen, sulfur, selenium, tellurium are non-metals. Polonium is metal and it is radioactive in nature and short-lived. Its half-life period is very less. Now let us see the remaining physical properties and trends. Electron gain enthalpy. Electron gain enthalpy decreases from sulfur to polonium. This is because size increases from sulfur to polonium. That is, additional electrons which are added feels lesser attraction, thus the nature of gaining electron becomes less. In oxygen, the size is least. Though the attractive force of nucleus is less, the additional electron coming from outside increases the repulsive forces, hence less EA when compared to other elements. Electronegativity decreases down the group. This is because increase in size decreases and effective nuclear charge decreases. Now let us discuss some more physical properties and their trends. Catnation. What is catnation? Catnation is the property in which atoms of the same element, large number of atoms of the same element, combine among themselves to form long chains. So we know that carbon has the greater tendency of catnation. And oxygen has a less tendency of catnation. About 2 or 3 atoms can form a long chain in certain compounds. Sulfur has a strong tendency to catnation and it forms polysulfides and polysulfuric acids. So this is a polysulfide and polysulfuric acid. Multiple bond formation. These elements form multiple bonds, but the tendency to form multiple bond decreases down the group. So multiple bonds are formed as shown here. In carbon disulfide, sulfur atoms can form multiple bonds with carbon. Carbon disulfide is a highly volatile organic solvent and it is moderately stable. Carbon diselenide, Se double bond C double bond Se, it decomposes very easily. Carbon ditelluride substance is not known. Oxidation states. Now let us discuss the oxidation states of 16th group elements. Oxidation state of oxygen in hydrogen peroxide. How do we calculate? See, oxidation state of hydrogen into 2 atoms plus oxidation state of oxygen into 2 atoms. Therefore, the total charge present on the neutral molecule is 0. So, plus 1 into 2 atoms plus oxidation state of oxygen into 2 atoms equal to 0. Thus, the oxidation state of oxygen in hydrogen peroxide is minus 1. In general, in all the substances, the oxidation state of oxygen is minus 2 as it takes 2 electrons from outside since it is a highly electronegative atom. So this is an exception. Oxidation state of oxygen in dioxygen difluoride. So oxidation state of oxygen dioxide, dioxin difluoride is plus 1. So this is the exceptional case where oxygen shows positive oxidation state. Oxidation state of oxygen in oxygen difluoride OF2. So here the oxidation state of oxygen in oxygen difluoride is plus 2. So these two are the compounds in which the oxygen shows oxidation state as positive. So this we discussed already. Elements of group 16th, they have Ns to Np4 general configuration and they need 2 electrons to complete the nearest inert gas configuration. Thus they can show -2 oxidation state. Oxygen shows -2 oxidation state as it is highly electronegative. Generally, it does not show any positive oxidation state except in two compounds. The exceptional cases when oxygen reacts with fluorine, it shows positive oxidation state. In OF2, oxygen difluoride, oxidation state of oxygen is +2. In H2O2, that is hydrogen peroxide, oxidation state of oxygen is -1. In O2F2, the oxidation state of oxygen is -1. Now, what is the oxidation state of oxygen in O2 molecule? It is 0. Oxidation state of oxygen in O2 molecule is 0. Oxidation states of other elements in the group. Remaining elements of 16th group, that is sulfur, selenium, tellurium, polonium, also show -2 oxidation state. And of course, the tendency to gain -2 oxidation state decreases down the group and this is due to the decrease in electronegativity and increase in size of the atom. These elements also show +2, +4, +6 oxidation states. Out of these, +4 and +6 oxidation states are shown because of the presence of d orbitals. +4 oxidation state is more common among all these. This is due to the stability of +4 oxidation state increases and stability of a +6 oxidation state decreases down the group due to inert pair effect. What is inert pair effect? The reluctance of s electrons to take part in the bond formation is known as inert pair effect. Sulfur, selenium, tellurium show +4 oxidation states in their dioxides and +6 oxidation state in the trioxide and hexafluorides. +4 oxidation state is also shown in their tetrafluorides. Anomalous behavior of oxygen. We have already studied in the periodic table that the second period element in every group shows a different behavior because of the small in size, high electronegative, and not having d subshell. Now let us see the anomalous behavior of oxygen of 16th group. Oxygen is highly electronegative element and it has small size, as we discussed already. The small size and high electronegativity of oxygen results in hydrogen bonding in water, whereas it is not seen in hydrogen sulfide. Due to the small size, intermolecular van der Waals forces are very weak. Hence, oxygen is in a gaseous state. It can form p-pi bond. The absence of d orbitals makes its covalency limits to 2, whereas in other elements of the same group, the covalency exceeds. Allotropy. What is allotropy? The phenomenon or the property of an element in which it is available in more than two or more forms, whose physical properties are different but chemical properties are same, and such a phenomenon or property is known as allotropy. Right, the definition is given here: the property of an element due to which it is available in two or more forms having different physical properties but same chemical properties is known as allotropy, and those forms are called allotropic forms. Sulfur is available in different forms, that is crystalline as well as amorphous forms. Crystalline forms of sulfur, allotropic crystalline forms of sulfur are rhombic and monoclinic. Amorphous forms are mainly plastic sulfur. Sulfur has tetraatomic. It has S8 molecule and S8 molecule has a crown structure. Apart from sulfur, even oxygen also has an allotropic form, that is ozone, O3 molecule. The crown structure of sulfur is given here. Allotropes of sulfur. Sulfur is available in two forms, crystalline allotropes and amorphous allotropes. Crystalline allotropes are rhombic and monoclinic sulfur. Monoclinic sulfur is also referred as prismatic or beta sulfur. Rhombic sulfur is also referred as alpha sulfur, whereas amorphous forms of allotropes are plastic, colloidal, and milk of sulfur. Now here the structures of rhombic and monoclinic sulfur are shown here. S8 molecule has a crown structure, rhombic sulfur has an octahedral shape, whereas monoclinic sulfur has a needle shaped crystals, and this is the shape of a crown structure here and here. Now let us see the differences between rhombic and monoclinic sulfur. Rhombic sulfur is also referred as alpha sulfur and monoclinic sulfur is also referred as beta sulfur. Melting point of rhombic 385.8 Kelvin and that of monoclinic is 393. Specific gravity of rhombic sulfur is 2.06 and specific gravity of monoclinic sulfur is 1.98. Solubility. Rhombic sulfur is insoluble in water but soluble in carbon disulfide. Monoclinic sulfur is also insoluble in water but soluble in carbon disulfide. Stability. Rhombic sulfur is stable below 369 Kelvin, whereas monoclinic sulfur is stable above 369 K. Then how do we prepare? Rhombic sulfur is prepared. The solution of roll sulfur. When the solution of roll sulfur is evaporated, then we get rhombic sulfur. Then how do we prepare monoclinic sulfur? Alpha sulfur, that is rhombic sulfur, is heated to get liquid. The liquid is poured out through the hole made on the crust on the top of the liquid to get needle shaped beta sulfur or monoclinic sulfur. So here, as we discussed here, the stability, rhombic sulfur is stable below 369, whereas monoclinic sulfur is stable above 369. Now let us understand the preparation of monoclinic sulfur from rhombic sulfur.
Monoclinic sulfur is only stable above 95.3 degrees Celsius, and needle-shaped crystals of the element can conveniently be prepared from molten roll sulfur. The sulfur is melted carefully and then allowed to cool. Once a solid crust is formed, the molten liquid inside is poured out through the small holes that are made in the crust. When the cooled solid is broken open, the monoclinic crystals can clearly be seen.
Let us conclude this topic with this. Thank you.